Hey everyone, welcome back. So in this video, we shall take a look at forecasting the ARMA process. So far, we looked in details at one step ahead predictor, right? That's what we did in the Durbin-Levinson algorithm. In general, we might be interested in the more general prediction. That's the M-step prediction. So property 3.3 in the textbook talks about that. So basically, if I want to predict the predictor of xn plus m has this notation. This x plus n plus m means we are predicting the n plus mth observation based on this n is basically we are predicting it based on the n observations. So we know that it's a linear combination which is given by this, and the property 3.3 tells us that these constants, the betas, have to satisfy the prediction equations. So this also ends up being the conditional mean of xn plus m given this. If you're not familiar with conditional means, you can just ignore you can just ignore this part a bit. Don't worry about it. Basically, this conditional mean is not the same as mean. So expectation of u given v is in general not the same as expectation of u. Okay, they are two different things. This is basically accounting for the fact that you've observed v. So u given v means v has been observed, and you're going to use this fact to calculate the expected value of u. So that's what this means. So we know we obtain the coefficients to minimize the prediction error. We'll run into matrix inversion issues. For one step ahead, we can bypass this inversion issue using the Durbin-Levinson algorithm. For an n plus m step, right, we cannot use the Durbin-Levinson, but we are going to look at a different way of obtaining predictions. For an n plus if you want to predict what's happening m steps later, and which will also avoid this matrix inversion problem. Okay, but for this we are going to assume that we have this complete history. So far we're assuming we know data from x1 to xn. Now we are going to assume that we know x0, x minus 1, and so on. So we have this entire infinite history. Of course, this is not very realistic, but we'll see that that is okay. Okay, even if it's not realistic, this works out. So the predictor of xn plus m based on this infinite past is nothing but this conditional expectation, or this expectation conditional on all of this infinite past. So this is conditioned on past n observations. This is conditioned on the infinitely many observations. So in general, these two are not the same, but if our n is large enough, then we can show that there's an n missing in the subscript, that this predictor based on past infinite values is a good enough approximation for this guy. So to obtain this estimator on past infinite values, we are going to look at the causal and invertible forms. This is the causal form, this is the invertible form. We've studied this before, so not getting into the details of that. So now we're going to take the conditional expectations in the causal equation, which is this guy. So conditional expectation of this given on the past infinite values is denoted by x tilde. So conditional expectation of this on the past infinite values is equal to x tilde. That's the notation. Now again, like expectation can be taken inside, conditional expectations can be taken inside. So we get conditional expectation of this is the conditional expectation of w's, which is here. Now we're going to use simple properties. So I'm going to assume my white noise W1, W2 are all independent, and we know that expectation of the white noise is 0. We know that. So now if I'm looking at conditional expectation of W3 given W3, This is just going to be W3. And this makes sense intuitively, right? So the conditional expectation of a random variable, if you observe it, it's the observation, right? It's this. So expectation of W3 given W3 is just W3. Expectation of W3 given W1, W2, W3 is also W3. Expectation of W3 given X1, X2, X3 is also W3. Why is this? Because X1, X2 and X3 encode information on W1, W2, W3, right? So all of these variables have information on the W's. Therefore, whether you're given, so observing this X is the same as observing W's. So therefore, this condition holds. Now, these are just intuitive explanations I'm giving. These are not proofs or anything. These are not rigorous. What I'm saying is not mathematically rigorous. Expectation of W4 given W3 is just expectation of W4, which is 0. So if I'm trying to, look at the mean of something in the future given this past, and these are independent, then this is just the same as mean of W4, and we know that is 0. Okay. So these are the properties we'll use right now to calculate this conditional mean. So what we have is Wt given xn is 0 if t is greater than n, right? That is if this is in the future. Wt given this is the same as Wt if t is less than n, right? So if we substitute it in this particular equation, in this particular equation, you get this. So the zeros go away and you're left with these terms, right? So let's see if j is equal to m, right? So expectation of wn given xn and backwards is just wn, right? So this holds for j is equal to m and so on. So if m is equal to 1, if j is equal to m plus 1, then you go one step back here, right? So you'll get n minus 1 here. So basically n minus 1 given xn and so on is just w, it's the random variable itself. So basically you can use these two properties, you get this particular representation. So now we take the conditional expectation of the invertible equation, and this is what we get, right? So we just take conditional expectation on each side. So if j is equal to 0, we get this. So we know that pi 0 is 1, and this would be expectation of n plus m given all of this, which is just x tilde n plus m, and then we have all of these other terms here, okay? So what we get is, so remember this is in the future, n plus m is in the future, this is the past. This conditional expectation is just expectation of wn plus m. W is white noise, therefore this is 0. So this is the expression that we get. Rearrange it, and then you can write x tilde n plus m. I put this on the other side. I'm splitting this sum into first m terms and then m onwards, okay? So it's split in this way. Why? Because m onwards, if a j is m and onwards, you basically so let's see, so if j is equal to m, then you have xn, and expectation of xn given all of this is just xn, okay? So you have these random variables and you have this x tilde here. So this is the equation that we are going to use to obtain x tilde n plus m, okay? So you can see that this is a predictor, and I also have predictors here. So again, you're going to first take m is equal to 1, obtain the predictors, m is equal to 2, and so on. And you'll keep on doing this till you hit x tilde n plus m. So this is also an iterative or a recursive equation where we start from m equal to 1 and we increase it up to the required value. So what is the prediction error for this x tilde estimator, right? So x tilde x n plus m can be written in this form. We basically, this is something we showed already, right? So let's go back. Oh. Not here. So if you go back 2 slides, yep, this is the one, right? So this is the equation that we already showed. So I'm using this now to calculate the prediction error. So okay, the slides are just jumping back and forth. Yeah, so this is the equation. So xn plus 1, this is what we want to predict, and this is the predictor, right? Difference between these two, this is the causal representation of xn plus 1, and this is just this upper equation here, and this is what you're left with. Okay, so the mean square prediction error is expectation of this square of this difference, and this ends up being just this. So sigma squared is the variance of your white noise, and you end up with this sum of sigma j squares. The sigma j's are again from this causal not sigma psi j's. Psi j's are from the causal representation. So now we look at long range forecast. Okay, so what is long range forecast? I'm trying to predict something that is happening way far into the future, right? So basically the m is converging to diverging to infinity. So m is super large. And so that's what you want to look at here. And say the ARMA series has a mean mu. So far we've been assuming it has mean 0, but even if it doesn't have, if it has a non-zero mean, it's not too hard. So we are just going to replace xn plus m with this. So we just subtract the mu. That's all we're going to do. Okay. So if you go by that, we know that x tilde n plus m is just mean plus. Okay. So I'm just adding this mu pops up into this equation. So this is now the predictor, and now the weights, right, the sigmas, they dampen to 0 exponentially, so they converge to 0 as m converges to as m goes to infinity. So why is that? So that's going to be a homework, or you're going to think about it in a homework assignment. Okay, so basically as m converges, as m goes to infinity, these constants go to 0, right? This entire sum goes to 0, and what we are left with is this predictor x tilde n plus m converges to this. So it makes sense, right? So if you're trying to predict something way into the future, the predictor just ends up being the mean, right? So we are not able to give a whole lot of information, but we are using the mean to predict something that's going to happen very much into the future. So remember, again, this was the formula we obtained for the prediction error in the previous slide, and we know that xn plus m again has this form. This is again from the previous slide. Okay, so this is basically the causal equation. So the variance of xn plus m, so this is the causal equation. Remember, variance is just basic rules about variance, right? So variance of w is a sigma square, and then we have this. So if you observe, these two terms are the same. So the prediction error, right, for this x tilde n plus m, if m is very, very large, the prediction error is this. And this ends up being the variance of xn plus m, right? So prediction error is the same as variance, and I'm going to call it as sigma square x. So everything that's happening on this particular slide is assuming that m goes to infinity. So that's the long range forecast. So the ARMA forecast settled to the mean, which was mu, as this m grows. So to summarize, when n is small, we can actually invert those equations and use property 3.3 for prediction. N is large, inverting equations can be a problem. So therefore we use this x tilde n plus m as an approximation. Okay. And the x tilde n plus m can be obtained using this equation. So this is the equation we'll actually use to obtain the predictor. Since we don't really observe all of this past history, right, we are going to use a truncated predictor. So when it actually comes to implementing this method, we don't have all of this. So what we are going to do is instead we are going to use this predictor. So x tilde, so this predictor at m steps ahead. I have this n now, so n means this is a truncated predictor, and we are predicting only based on the first n observations. Okay. So this is given as this. So what I'm saying is so this term is the same as this. So compare these two expressions, right? This is based on the entire past history. This is a truncated predictor, and this is assuming we don't really have all of these observations. So this is the same, right? So in this first summation, j goes from 1 to m minus 1. J is equal to 1. This is xn. That's not going into the past history. If j is equal to m minus 1, we get, so if you substitute m minus 1, we're left with n plus 1. So we're not going into the past either. So we have these terms here. This is where we start going into this x0, x minus 1, x minus 2, and so far here. Okay. So you see we are limiting this sum here. Okay, so here we go all the way to infinity, but here we restrict ourselves from this range. J goes from m to n plus m minus 1. So we're not going all the way in the past, we're only going here. And if j takes value, let's see, n plus m minus 1, so this is going to be minus n minus m plus 1. So you're going to be left with x1. X1 is as far back as we want to go, right? So the last term here you're left with is x1. Here you go to x minus infinity. This is the truncated predictor. This is what we execute in an actual application. So now so before we take a look at an example, this is truncated prediction for ARMA models. So again, this is just another bunch of equations. So if you have noticed that there's a pattern, right? There's different ways of suggesting what kind of predictions we can do. And for each different way, you have to kind of look at what different properties might follow. So this is just another way of predicting. And this is also a truncated prediction. So what we're doing here, so we have an ARMA PQ model. Tilde, so we have x tilde n plus 1 m, and so we are going to past, we have this phi 1 x one step back, phi p all the way, you have this p steps back. So this has this ARMA form, but these are all predictors. So you notice this is tilde, we have tilde here. And same thing here. So normally this would correspond to the moving average part of the ARMA model, but instead of w's, we have these predicted values substituted. So in this truncated prediction for ARMA, right, you basically write the ARMA model, but then you substitute the x's with the predictions, right? You substitute the w's also with the predictions. So that's a way to remember what is going on here. So remember these conditions. So if we're trying to, so t is greater than n. So if you're trying to predict something in the future, so w tilde x tn for t greater than n is 0, right? So this is something you need to be watch out for. So how are we going to actually predict this W tilde? So this W tildes are given by these equations. So you kind of need to remember this, but it's not that you need to remember this blindly. There are some patterns, there is some logic that is going on here, right? So in this equation, we write the ARMA, but we replace the X with this tilde predictors, or the W's with also the predictors. Now we know how to calculate this X tildes. We don't know what to do with the W tildes. So the W tildes come from this equation. Okay. So basically, so it comes from this equation. So let's just look at an example. It's easiest to figure out what's happening with an example. So we have an ARMA 1-1 model here. This is just the basic ARMA model equation. So for m is equal to 1, we have this. So m is equal to 1, let's go up. Let's keep all of this. Okay. So m is equal to 1, that means x tilde n plus 1 m is equal to, now this is an ARMA 1-1. So we only have this phi times x tilde n, remember m is equal to 1 right now, so this is what we're left with. So all of these other phi's are zeros, and then we have this. Okay, so we just have one theta, right? This is an m ARMA 1-1. So m is equal to 1, we have basically theta w tilde n n. So that's the equation we have here. Theta this one, theta w tilde n n. So if you go back and substitute m is equal to 1, this is exactly what you get. Now for m greater than equal to 2, this is the equation again you get. So let's see why this is true. So say m is equal to true, m is equal to 2. Go back. Okay, so m is 2. So we have phi 1 x tilde n plus m minus 1, so that's 1 here, right? N plus 1. But let's see what happens to the w's more importantly. So if m is equal to 2, that means I have w n plus 1 n, right? So this lower subscript is greater than this n. So if m is greater than equal to 2, what happens is this lower subscript becomes larger than n for the w's, and we know if that is the case, the w's are 0, the w tildes are 0. So for m greater than equal to 2, this is the equation you get. And now how do you actually calculate this w tilde nn, right? So you can think of it this way. So you have the so this is the equation we'll be using for it. Okay, this is the equation. So we have this. So let's see, I think I forgot to add. Yeah. So phi beta x and t, and remember phi beta, this is an ARMA 1-1, right? So phi beta is just going to be 1 minus phi 1 x t minus 1n, right? And then we have these remaining terms here. So I should have had this tilde here. This is missing, right? So this is the autoregressive polynomial part. This is the remaining part. So to calculate, there is a tilde missing here as well. So to calculate this W tilde Tn, we need this equation. So we need to so we initialize these W's and this x naught to 0. Okay, so let's see. Oh, I have the equation here. This is the equation we have. So plug in t is equal to 1. So t is equal to 1. We get x1 minus phi x naught minus theta w0 n. But we are initializing this to 0. And this is also 0. So we have x1. This is something we have observed, right? So therefore, we have w tilde 1n. For 2n, we just plug in. We look at this equation and we plug in t is equal to 2. But we have x2, we have x1, and we have this w tilde 1n as well. So therefore, we can calculate this, and you can continue in this fashion, right, until we get w tilde nn. So you continue until we get this term. So this is the way to execute this truncation predictors. So once we have predictors, right, once you're predicting something, the next thing is can we construct the prediction intervals? Okay, so the 1 minus alpha prediction level prediction intervals have this form. So you have your predictor plus minus this c times this constant times square root of this prediction error. Okay, and the C alpha by 2 is chosen to get the desired degree of confidence. So this is a little bit of a recap of interval building, of confidence intervals that you've done in previous classes. So basically the C alpha by 2 comes from the cutoff. So for example, if you want a 95% prediction interval, and if our data is Gaussian, then we look at this and then we get this cutoff, right? So we want a 95% prediction interval. So this entire area should be 95%. That means I have 5% outside, 25% here, 25% here. You get from a standard normal distribution, you'll get this cutoff so that this area is 25%, and that's your C. It turns out to be 1.96. So this is a way to get prediction intervals, right? So that's all in this video. So far we were assuming that the phi's and the thetas in the models, right, in the ARMA models were known. And if they are known, how do we do the forecasting? However, it's unlikely that we know the phi and the theta, and we need to estimate that from the data, right? So we look at some estimation material in the next video. See ya.